Something that you learn in a lot of the times middle school, you learn it again in high school, you learn it again in some college classes like this one, is the Pythagorean theorem. Pythagorean theorem. And the Pythagorean theorem is just a squared plus b squared equals c squared when you're talking about right triangles. But you're not often given a proof, so I just wanted to take a minute in this class, since we prove a lot of things in this class and use a lot of logic, to do one of my favorite Pythagorean theorem proofs. There are literally thousands of proofs of this, but this one's geometric and it makes a lot of sense with what we've been learning in our class. So, the first thing we need is a little definition. We need to know this triangle. In this triangle, we're going to have the short side being A, the long side being B, and the hypotenuse being C, as given. And we're going to assume, and this is my best attempt at drawing straight triangles, we're going to assume that these are right triangles. 4 right triangles just set up in kind of a rectangle. In fact, since these, we'll see that since we have the same short side, long side, as right here, short side, long side, we're actually going to not have a rectangle. It's going to be more than a rectangle, a square. So, let's try to prove that a squared plus b squared equals c squared using a couple of pictures. Here's our first picture. And what we're going to be using is area. We know the formula for the area of a square. And let's see what we get. So let's say I want the area of this square. I have a little a here, and a b here, and another a here, and a b here, and an a here, and a b here, and an a here, and a b here. And our inside is just a bunch of c's. And not only that, but our inside is 4 side lengths that are all length c. And how do we find the area of a square or a rectangle or a shape that has 4 side lengths that are all length c? Well, this is just going to be a square inside itself. So we have that is going to be this inner square is going to be c squared. And what's our total area here? What's our total area? Well, each side length is going to be a plus b. We have an a plus b there. We also have an a plus b here, or b plus a if you're getting specific, but that can just be switched to being an a plus b. And we have an a plus b here. We have an a plus b here. So we have a bigger square on the outside. I'll mark it. It's this square on the outside. And what's the area of that square? So we have the area of the inner square, the green square, is c squared, but the area of the red square is going to be a plus b squared. So now let's take those two things together, and let's say that the area, let's say now we're looking for just the area of the triangles. Those will be in yellow here. Here's one triangle, here's another triangle. Let's say we're looking for this area, the area of the triangles. And you'll see why in a little bit. Well, the area of the triangles is going to be the total area, or the box's area, the red area, minus the green area. Because that's the area inside that is not a part of the triangles. So if I assert to you that this here is the total area, and this here is the part of the area that is not included in the triangles, then you put those two things together, and the area of the triangles is going to be this one minus this one. So we have something here. We have that the area of the given triangles, let's say the area of the 4 triangles, is equal to a plus b squared minus c squared. And now we're going to do a similar thing. We're going to do something a little different. We're going to use a different picture. And here's our picture. Same exact triangles. They're just set up in a different way. And in fact, they're the same triangles. And since they're the same triangles, if I make the big square with these, we're going to have the same area as the other triangle because I have a side B here, a side A here, a side, you see that this is B, so this is B, this is also B, this is A, this is B, this is A, and this is A. We have the same square. The square where the side lengths are AB, AB. So the area of the big square, once again, the square in blue is going to be A plus B squared. That's the area of the big square. But what if, once again, I just want the area of these little triangles? Should do that in a different color. Let's do that in green. I want the area that's just in these triangles. I want this area. Well, in order to find that area, I need to figure out the area of the empty space. So let's start with this one. Let's start with the square in red. Well, we see pretty quickly that this side length is B, this side length is B, the area of this one's going to be B squared. And then let's do this one right here, this area in yellow. We see that this is an area of A times A, which is going to be A squared. So we see that our area here, our area is equal to A plus B squared minus A squared minus B squared. That's the area of our big square. But like I said before, if I zoom out, these are the same square. You can kind of see it. I have my A's and B's mixed up in some places, but these two squares are equal to each other. I'll put a big equal sign. They're equal to each other. And we have two equations for their area. So if you have two things that you know are equal to each other, I can just plug in this area for this A. I can combine our two equations. And I can say that we have A plus B squared minus C squared is equal to A plus B squared minus A squared minus B squared. And let's just section this off to make it a little easier to look at. Section it off in purple. And now you can kind of see our proof of the Pythagorean theorem peeking out. I can subtract the whole A plus B squared term. When I started this, you might have thought we were going to have to do some multiplying out or foiling, but we don't, because we can subtract this from both sides. The A plus B squared cancels from both sides, and what am I left with? I'm left with negative C squared is equal to negative A squared minus B squared. Divide both sides by a -1 or multiply both sides by a -1, and we have exactly C squared equals A squared plus B squared. And this is one of my favorite proofs because you see it in the squares. You see that the two squares are equal, and in order to prove the Pythagorean theorem, all we have to do is draw two different combinations of 4 of these triangles. And we arrive at A squared plus B squared equals C squared, which is the Pythagorean theorem.